Hello everyone. In this AV, we would be talking about the chapter called heat transfer. As you already know that when heat flows from one place to another or from one body to another body, this is known as the transfer of heat or heat transfer. Heat is generally transferred by three means, namely conduction, convection and radiation. So we would be talking about all these three methods in detail and would know how it takes place and what is the phenomenon behind it. In conduction, there are two ways of heat transfer. Firstly, to understand this, if we assume that we have a rod and we have the particles of the rod which are present here, and it's present all over. Now this end of the rod is heated up. If we heat up this end of the rod, what happens is the temperature of these molecules rises up. Now once the temperature of these molecules rises up, they are in contact with the other molecules which are comparatively at a lower temperature than these molecules. So by simple means of contact, the heat will flow from higher to lower end, or from the molecule which is at a higher temperature to a molecule which is at a lower temperature. And this phenomena will continue and heat will be transferred from one end to the other end. This is one method of conduction, and the heat flows from a region of higher temperature to the region of lower temperature by simple means of contact. Now here what we have to keep in mind is these molecules are not leaving their place. They are transferring the heat by simple means of contact. Another phenomenon or another way of heat conduction in the method of conduction is we have something called free electrons in metals. Now these free electrons, they are not bound in the metal, they are free to move around. So when we start heating at one end of the metal, what happens is these electrons, they gain energy and their average kinetic energy increases. Once their average kinetic energy increases, they are more energetic and they collide with another electron with more energy. The moment they collide with the other electrons, what happens is they pass on some energy to the other electrons. Now this electron after collision has gained some energy and now its average kinetic energy increases. Now this will vibrate or collide with more energy. So this method continues, and finally by the method of collision heat is transferred. This is also a way heat is transferred in conduction. But please keep in mind that here the molecules are not leaving their place. In this case, it's not the molecules but the free electrons which are vibrating more or which are colliding with the other electrons. So conduction is defined as the process of heat transfer or heat transmission in which the particle of the body do not leave their position. This is conduction. Now when we talk about convection, it generally takes place in liquids and gases, but conduction takes place in solids and in mercury, but can also take place in liquid and gases. To understand convection, consider that we have a fluid in a jar and we start heating it. Now the fluid can be a liquid or a gas. So once we heat it, what happens is the temperature of the fluid at the lower region rises up, and once the temperature of this fluid in the lower region rises up, its density becomes lesser and lesser. So if the density becomes less, these liquids will rise up, and once these liquids or these fluids will rise up, their place will be taken up by the fluid present in the upper region. So this layer goes up and this layer takes the place of this layer and it becomes the bottommost layer. Now that layer will be heated up again. Once the heat energy increases, then we have this layer, their density will be less and it will go up. Again the same process will be repeated, and in this way a time will come when heat will be thoroughly transferred throughout the fluid. In this case, what we observe is the molecules of the fluid are moving around to transfer the heat. Now this is the process of convection. The process of heat transmission in which the particles of the fluid move is called convection, and it generally takes place in liquids and gases. The third method of heat transfer is known as radiation. Now radiation is a process in which heat is generally transferred in form of electromagnetic waves from a hot body to a colder body or a body at a lower temperature. Now the example here can be the heat radiation from sun reaches the earth or reaches us by the process of radiation, and in this process we do not require any medium for the transfer of heat. Another thing we have to keep in mind is for conduction and convection, the heat transmission can be in a zigzag manner, but for radiation the heat transmission path is a straight line. Now what happens when a metal rod is heated? So we go to conduction of heat in a metal rod. Now when we heat a metal rod, suppose we assume that Q amount of heat is supplied to the metal rod. Q1 or a certain amount of heat, which we denote it as Q1, will be absorbed by the area of cross section, this area of cross section, and Q2 is the amount of heat which will be given to the atmosphere by the method of convection. So after losing Q1 and Q2 amount of heat, the remaining, that is Q3, will be passed on to the next portion. So the total heat Q is given as Q1 plus Q2 plus Q3. Now in this process or at this point, this rod is at a variable state. Now variable state is a state where the temperature at different cross sections of the rod keep on increasing with time, and then will come a state when this rod will reach its so-called steady state, where not the temperature will be the same at every segment, but the temperature will be constant for each and every segment. It will remain steady. Now that will be known as the steady state. If we assume that we have this rod and this hot end of the rod is maintained at a constant temperature. So if we can maintain this at a constant temperature, the heat absorbed by the cross section area, that is Q1, will be 0. The cross sectional area will not conduct any heat. There will be only one loss, that is Q2, which will be released in the atmosphere by the process of convection. So if Q is the amount of heat which is transferred from the hotter end, then we have Q2 amount of heat which will be lost to the atmosphere, and then remaining, that is Q3, will be transferred to the next area of cross section. Again some energy will be lost to the atmosphere and remaining will be transferred to the next area of cross section. Some will be again lost to the atmosphere and remaining will be passed on to the next area of cross section, and the process continues. Now this is the reason why we have a lesser amount of heat passing to the next area of cross section, and there will come a time when all these thermometers will record a constant temperature. It will not be the same throughout. As you can see here, this is the highest, then the temperature decreases, it decreases more, and slowly we have a final drop in the temperature. But a time will come when they will show the constant reading. That will be known as the steady state. In this state, the rate of conduction of heat in the rod will depend on the conductivity of this material of the rod, about which you have studied in class 10. Now the amount of heat which is being allowed by this metal rod or this rod is known as the conductivity or thermal conductivity. Means how much heat can it conduct, or how much heat will it allow to pass through it. Now we will try to find out the coefficient of thermal conductivity. So we assume that we have taken a parallel faced slab where we are giving Q1 amount of heat and the same amount of heat where we are giving Q amount of heat, and Q amount of heat is only leaving from the other cross-sectional area. Now the total cross-sectional area is A and the length of this slab is L. Theta 1 is the temperature of the first phase of this slab and theta 2 is the temperature of the second phase of this slab. Now theta 1 is at the higher temperature and theta 2 is obviously at the lower temperature. If the amount of heat entering and the amount of heat leaving are the same, that is Q, then experimentally it can be showed that the heat is directly proportional to the area of cross section, and it will also be directly proportional to the temperature difference between two phases. And since we have the first phase which is at temperature theta 1, which is the higher temperature, then the second phase, that is theta 2, so the difference in temperature will be theta 1 minus theta 2. So Q is directly proportional to theta 1 minus theta 2, that is the temperature difference. Then Q is also directly proportional to the temperature. That means for the more the time heat is supplied, more will be the amount of heat. Now finally we have the heat supplied or the total heat inversely proportional to the length of the slab, because you have seen that for every area of cross section there is some amount of heat lost. So if we have L which is very long, or the length of the slab is long, then there will be more heat lost. Now if we combine all these 3 or 4 things, then we have Q is directly proportional to, or Q is the heat, is directly proportional to area of cross section, theta 1 minus theta 2, which is the temperature difference, and directly proportional to the temperature but inversely proportional to L. So the equation becomes Q is proportional to A, theta 1 minus theta 2 multiplied by T upon L. Now we are aware that if we want to remove the proportionality sign and we want to bring in equal to sign, then we have to introduce a constant, and in this case the constant happens to be K, which is known as the coefficient of thermal conductivity, which is denoted as K. And this K, or the coefficient of thermal conductivity, depends upon the material of the slab, and K, or the coefficient of thermal conductivity, is defined as the amount of heat that flows in unit time through unit area of a material perpendicular to the flow under unit temperature when the steady state has been reached. Please remember, steady state means all the different cross sections will maintain the same temperature. It will not be equal, but the temperature will be the same. Now if the heat escapes out from the sides or face of the slab, then it would be represented as the heat flowing will be dq equal to minus ka d theta upon dx multiplied by dt, because this heat loss will be for a very small time. So, and the heat loss would be very small, so that small heat loss is represented as dq. Time is very small, so it's represented as dt. Change in temperature is denoted as d theta upon dx, which is the small area of, or small length, sorry. So this minus sign indicates that the temperature will always decrease in the direction of heat flow. If you remember, then we can see that for every area of cross section the heat flow is decreasing as there is a loss of heat to the atmosphere by the process of convection. And the SI unit for this K is watt per meter per Kelvin. Now, as we have seen the rate of heat flow in one slab, let us take two slabs and join them and see what will be the rate of flow of heat, how much heat will be allowed to flow, what will be the temperature at the interface, and what will be the thermal conductivity if we consider both these slabs as one slab. Now, when we have more than one, that is two slabs, so we can join them in series, or it can be joined in parallel, that is one on top of the other. So first we will see when these slabs are joined in series. So we assume that we have taken two slabs and we have joined them in series. Both these slabs have area of cross section as A, and this is the interface where they have been joined. So we assume that the length of the first slab is L1 and length of the second slab is L2. Now, after the steady state has been reached, we assume that the temperature at this phase, the open phase, the first open phase, is theta 1, which is the higher temperature, and the second open phase is theta 2, which is the lower temperature compared to theta 1, and theta is the temperature at the interface or the phase joining the two slabs. Now, at steady state, the rate of flow of heat in both the slabs will be the same. So we have heat is equal to Q upon T. We use this formula for Q. Q equal to Ka theta 1 minus theta 2 multiplied by T upon L. So here this portion represents the first slab. So for first slab, please check. Coefficient of thermal conductivity for the first slab is K1. So we have K1. A is the area of cross section multiplied by temperature difference. So general formula says temperature of the first phase minus the temperature of the second phase. That is, first phase is theta 1, second phase is theta 2. So we have theta 1 minus theta 2. Sorry, theta 1 minus theta multiplied by T, and then we have a T in the denominator, so that T and T will cancel out, and length is L1. Similarly, for the second slab, the coefficient of thermal conductivity is K2, so we have K2 multiplied by the area of cross section, that is A only, and temperature of the first phase minus the temperature of the second phase. So first phase here is theta minus theta 2 upon the length, that is L2. So since at steady state the rate of heat flow in both the slabs will be the same, so we equate these two. So it becomes K1 upon L1 theta 1 minus theta equal to K2 upon L2 theta minus theta 2. In case you don't understand, then you can see it here. What we have done is this A and this A gets cancelled out. So we have K1 theta 1 minus theta upon L1 equal to K2 theta minus theta 2 upon L2. This is what we have here. Now after this, there are a few steps in between these two, so that I have explained here. You can check. After cancelling area, we multiply K1 inside. So if we multiply K1 inside, then we will have K1 theta 1 minus K1 theta upon this L1 equal to K2 multiplied by theta gives me K2 theta minus K2 multiplied by theta 2 is K2 theta 2 upon L2. Now we write these denominators separately with each term of the numerator. So we get K1 theta 1 upon L1 minus K1 theta upon L1 equal to K2 theta upon L2 minus K2 theta 2 upon L2. Now what we do is we take this term containing theta with this term containing theta. We bring them together, and this theta 2 we take it to the other side. So we have K1 theta 1 L1 plus this minus K2 theta 2 L2 coming to the left hand side becomes plus K2 theta 2 L2 is equal to K2 theta upon L2 remains as it is, and this minus K1 theta upon L1, when we take it to the right hand side, it becomes plus. After this side remains as it is, but from here we take theta common. Once we take theta common, then we have K2 upon L2 and K1 upon L1. So K1 upon L1 we are writing first, and then we are writing K2 upon L2 as A plus B is equal to B plus A. Now we have to find the value of theta. So we keep theta on one side and remaining things are taken to the other side. So theta is equal to, this portion remains as it is, K1 theta 1 upon L1 plus K2 theta 2 upon L2 divided by this portion K1 upon L1 plus K2 upon L2. So when we take LCM, L2 will be multiplied by this and L1 will be multiplied by this. So we have this equation, and in the denominator for this we have L1 multiplied by L2. So this is the upper part, and for the lower part we have again L2 will be multiplied by K1 and L1 will be multiplied by K2. So we have K1 L2 plus K2 L1 upon L1 L2. Now here this L1 L2 and this L1 L2 cancel out, and we have theta is equal to K1 theta 1 L2 plus K2 theta 2 L1 upon K1 L2 plus K2 L1. This is your equation 2 in the textbook. So they have jumped few steps which I have shown you on that page. Now if we assume that both the slabs are of the same length, so they will not be L1 and L2, they will be L and L. So L1 is equal to L2 is equal to L. So this equation will be modified as, in place of L1 and L2 it will be replaced by L. So we will have L here and L here. Here also we will have just L, and here also we will just have L. So if L1 and L2 equal to L, this is the special case, then they will be written as L, no L1 and L2 anymore. So from the numerator we can take L common. If we take L common, then below also we can take L common from the denominator, and they will cancel out, and our equation for theta will be reduced to K1 theta 1 plus K2 theta 2 upon K1 plus K2. This is the equation 3 of the textbook. Now this is the temperature of the interface, that is theta, we have found out. So after finding the temperature of the interface, that is theta, if we substitute the value of theta from this equation, that is equation 2, in the first equation, then we can find out the value of H, that is the heat transferred. Now for that we have a look at the equation 1. We will be assuming H equal to Q upon T equal to K1A theta 1 minus theta upon L1. We will be considering only this equation. So in place of theta we will be substituting the value of theta from this equation, and our equation will look something like this. So H is equal to Q upon T K1A upon L1 theta 1 minus theta. So in place of theta we write K1 theta 1 L2 plus K2 theta 2 L1 divided by K1 L2 plus K2 L1. Now we take LCM, and whatever is the remaining part we leave it as it is. So this whole thing will be multiplied with theta 1. So we have K1 L2 multiplied by theta 1, so becomes K1 L2 theta 1 plus K2 L1 multiplied by theta 1 becomes K2 L1 theta 1. Minus is multiplied with both these terms, so they become minus and minus. So here we find that K1 theta 1 L2 and K1 theta 1 L2, they are same with opposite sign, so they cancel out, and we are left with K2 outside remains the same. K1A upon L1 is equal to K2 L1 theta 1 minus K2 theta 2 upon L1 divided by K1 L2 plus K2 L1. Now we multiplied the quantities outside with the quantities inside. So the equation looks something like H equal to K1 K2 A theta 1. Why? Because L1 is taken out as common, and with this L1 it gets cancelled out, and minus these two terms, that is K2 theta 2 and K1A from the outside. So this becomes the new term, and the denominator remains the same, that is K1 L2 plus K2 L1. Now what we do is we take K1, K2 and A common from both the terms present in the numerator. So we have H is equal to K1 K2 A multiplied by theta 1, this term, minus theta 2 is the remaining term from the next portion, upon the denominator, that is K1 L2 plus K2 L1. Now what we do is we divide the numerator and denominator by K1 and K2. So after dividing we have H is equal to, we divide all the terms with K1 and K2. So this K1 K2 and this K1 K2 cancels out, and in the numerator we are left with A theta 1 minus theta 2. So A theta 1 minus theta 2. Here in denominator K1 and K1 will cancel out. In this portion K2 and K2 will cancel out. So we have L2 upon K2 plus L1 upon K1. So again, as A plus B is equal to B plus A, we are writing this term first. So it becomes L1 upon K1 plus L2 upon K2. This is the equation 4 in your textbook. That is this equation. Now this is what we have found out the value of heat transferred. Now finally, to find the equivalent thermal conductivity of this whole slab, that means what will be the thermal conductivity if we consider this as one slab and not two different slabs. So for that again we use the formula H is equal to Q upon T, which is equal to Ka. Now here in this case temperature difference becomes temperature of the first phase, that is theta 1, minus the temperature of the second phase, that is theta 2. So we are writing Ka theta 1 minus theta 2 upon L1 plus L2. This is marked as equation 5. Now we compare equation 4 and 5 to find out the value of equivalent thermal conductivity. What is equivalent thermal conductivity? That is denoted by the term K. So we compare equation 4 and 5. So here we use the equation H equal to Q upon T. So Ka theta 1 minus theta 2 upon L1 plus L2. This is equation 5. Comparing it with equation 4, that is this equation, this is equation 4, we get the value of K as K equal to K1 K2 L1 plus L2 upon K2 L1 plus K1 upon L2. In case you have any problem understanding how we get this part, then you can consider writing equation 5 and equation 4 and substituting them against each other. What we will find is certain things will cancel out and we have to find out the value of K. So A and A will cancel out, and then to find the value of K, just keep K on one side and take rest of the terms on the other side. Then you will find that you get this equation. So this is the value of K, that is coefficient of thermal conductivity. Again, special case, if L1 equal to L2 is equal to L, that means the length of the slab is taken as L. So all L1 and L2 will be replaced as L. So here L1 plus L2, we will write L plus L, that is 2L. So we have here 2L, and below L and L, L1 and L2 will be replaced as L. So that L can be taken out as common. So L and L will be cancelled out, and the coefficient of thermal conductivity when both the lengths are same will be equal to K equal to 2 K1 K2. That means the thermal conductivities of the first slab multiplied by the coefficient of thermal conductivity of the second slab divided by sum of the coefficient of the thermal conductivity of the first and second slab. So this is the equation for the coefficient of thermal conductivity when two slabs are joined in series. Now we will see what will happen if the two slabs are joined in parallel. Now if two slabs are joined in parallel, we refer to this figure. In the previous case we had different length as L1 and L2. Here the length of the slab remains the same, and we have placed two slabs one on top of the other. So we find that here area of cross section of the first slab is A1 and of the second slab is A2. Heat supplied is Q1 and Q2, and coefficient of thermal conductivity of the first slab is K1 and of the second slab is K2, and the temperature of the first phase is theta 1 and temperature of the second phase is theta 2. Now again using the formula for the first slab which is on top, H1 is the heat or rate of flow of heat is equal to Q1 upon T. So this is equal to K1 into A1. Now here this is the interface. So that is, we are not denoting it with anything because the heat will flow from this direction to this direction. So here our phases will be theta 1 and theta 2 only, no theta. So we have K1 A1 theta 1 minus theta 2 upon L. Now for the second slab, the rate of flow of heat will be denoted as H2, which is equal to Q2 upon T. So here we have K2 A2, temperature difference remains the same, that is theta 1 minus theta 2 upon L. Now to find out the combined flow of heat or the combined rate of flow of heat, we simply add both of these, H1 plus H2. So the combined rate of flow of heat is H equal to H1 plus H2. So we simply add this with this. So what we find is theta 1 minus theta 2 is common. So that is written outside the bracket, and we have K1 A1 plus K2 A2 from this equation, and L is common in both. So L we write together only. Now this is the rate at which the heat will flow in this combination, that is in a combination when the two slabs are joined in parallel. Now what will be the equivalent thermal conductivity? That is K. So we substitute this with Q upon T. So comparing this with equation 1, that is this equation, what we get is KA1 plus A2, because if you again equate these two equations, theta 1 minus theta 2 and theta 1 minus theta 2 will get cancelled out. So we have KA1 plus A2, L and L will also cancel out, is equal to this part, K1A1 plus K2A2. So from here we can simply find out the value of K, that is the equivalent thermal conductivity, by simply taking A1 plus A2 to the right hand side. So this becomes K1A1 plus K2A2 divided by A1 plus A2. Now in this, the special case would be if the area of cross section A1 and A2 are the same. So if that is the case, then A1 and A2 will be the same. So we can write it as A can be taken as common, and here A plus A will be 2A, so that A in the numerator and A in the denominator will cancel out, and this equation will reduce to K is equal to K1 plus K2 upon 2. Now that's all in this AV. For the remaining part of the chapter we will have another AV. Thank you.